Okay, so today, we're not going to be solving a bunch of math problems. No, we're here to learn an entirely new language. And I don't mean French or Spanish. This is a language that describes the very fabric of reality. Everything from a planet's orbit to how populations grow. We're diving into the language of differential equations.
I mean, listen to that. They constitute the syntax of evolution. That just gets right to the heart of it, doesn't it? See, differential equations aren't just about numbers on a page. They're the fundamental rules, the grammar, really, that governs how literally everything in the universe changes and evolves over time.
All right, so if we're going to learn this language, we've got to start with the basics, right? The grammar. What actually makes it so different from the math you might already be familiar with? Okay, this is a really cool way to think about it. If you've taken calculus, you know it's all about how change occurs. It's like the verb of motion, right? The action word describing what's happening at a single instant. But differential equations, well, they're the rules of the story. They're the whole narrative. They don't just tell you that something is changing. They tell you why and how that change governs the behavior of the entire system.
And this right here, this is the absolute core of it all. The differential is that fundamental piece of grammar. It's the little link that connects an object's current state to its rate of change. Think of it like a law that says, hey, because you are here, this is exactly how fast you must be moving. It's a dependency. And that's what makes it so powerful. This is why we can call it a universal language, because it doesn't matter what you're talking about. Heat spreading through metal, a virus moving through a population, or planets swirling around a star. The underlying mechanism, that fundamental grammar of change, is exactly the same. It's incredible.
Okay, but here's the thing. A set of rules is just abstract, right? It's just an idea. To tell a specific story, that equation needs a world to live in. It needs context.
I mean, think about it. How does any story begin? It has to start somewhere, doesn't it? A hero doesn't just pop into existence in the middle of their quest. They have a beginning, a starting point where their journey kicks off. Well, that's exactly what initial conditions are. They are the genesis of motion. They tell us, okay, at time zero, here's where the object was, and here's how fast it was going. Without that starting point, the rules of change just give you a whole cloud of possibilities, not one single unique story. But, a starting point isn't quite enough, is it? Our hero also needs a world to operate in, a playground, maybe, with defined edges and rules they can't break. And that's where boundary conditions come in. These are the edges that give the system its shape, the walls of the room, the limits of its universe. So, for example, if you're heating a metal rod but the ends are insulated, well, the heat can't escape, right? Those are the boundaries. They define the world the change is happening in. And this gets at a really deep, almost philosophical point. It's called ontology through constraint. A system only gets its reality, its actual identity, through its limits. It becomes what it is because of what it's not allowed to do.
All right, so we've got our rules, we've got our world. Now let's get to the really fun part, exploring the huge variety of stories this language can actually tell. And believe me, they range from the beautifully simple and predictable to the wildly chaotic.
And this whole process has a name. It's the art of modeling. It's basically being a translator, taking a messy, complex, chaotic system from the real world and translating its behavior into the precise formal language of change. So when we model things, we basically find two kinds of systems. First, you've got your linear systems. These are the nice ones. They're predictable, they're stable. The effect is proportional to the cause. You double the input, you get double the output. Simple, right? But then you have nonlinear systems. And oh boy, this is where things get really interesting. This is the realm of chaos, of emergence, where one tiny little change can lead to massive, totally unpredictable effects. And the crazy part is, most of the real world is nonlinear. This is the math that describes how a flock of birds just knows how to form those incredible patterns, or how ecosystems evolve. It's the math behind the famous butterfly effect, where a single butterfly flapping its wings could, theoretically start a hurricane. It's literally the mathematics of surprise. So what do you do when these systems get just way too complex to solve perfectly? I mean, what then? Well, we do something really, really clever. We approximate. We basically take the smooth, continuous flow of reality and chop it up into tiny, manageable, computable steps. And the simplest way to do that is called Euler's method. It's basically a little algorithm, a recipe for following the flow.
It's super simple. You start at a point you know. You figure out the direction of change, the slope. You take one tiny little step in that direction, and then you just do it again, and again, and again. And by connecting all those tiny straight lines, you can get a pretty good approximation of a really complex curve.
Now, approximating is great. It's super powerful, but it's not the holy grail. The ultimate prize, the thing everyone is searching for, is a perfect, elegant, exact solution. It's about cracking the code of the system completely. And that's what we call an analytical solution. It's not an approximation, it's a single, beautiful formula that perfectly describes a system's behavior for all time. When you find one of these, it's like achieving complete determinism. You know everything. Its past, its present, and its future, all laid out.
So you can see that the search for these solutions is more than just math. It's really a quest for total understanding. It's that magical moment, that aha moment, when all the complexity just snaps into focus and it's all captured by one perfect logical statement. It's a moment of pure, total clarity. So, we've come on this whole journey. We've got the rules, the world, the story, but what's the final result? What's the output? What is the actual yield of our mathematical story?
Well, the solution, the yield, is the tangible thing at the end. It's where the abstract rules finally become real. So if your equation describes the flight of a baseball, the yield is the actual path it takes through the air. It's the moment when the hidden process is finally made visible.
But here's a fascinating twist. Sometimes the most profound solution of all is zero. And the zero solution isn't just a lack of an answer. No, it is the answer. It represents perfect equilibrium, a kind of stillness within motion. It's a system in perfect balance, just holding all its potential completely at rest, just waiting for a nudge.
And that really brings us to our final thought. What we've seen today is that change isn't random at all. It follows this deep, underlying grammar. This amazing language lets us translate the messy, chaotic real world into these elegant, formal structures. So I want to leave you with this question. If the entire universe is governed by this syntax, what grand story do you think it's writing?